Let's look at the Laplace transform of a step function. Why use Laplace transforms? They enable us to solve differential equations involving discontinuous functions. Many of the things we've done with Laplace transforms can be done using other methods, but discontinuous functions, that's where Laplace transforms really shine. For a is greater than 0, define the function u of t minus a equals 0 for t between 0 and a, and 1 if t is greater than or equal to a. Here's what the graph looks like. This is straight from our textbook. Notice it's what we call a step function. Between 0 and a, it's 0, and then at t equals a, it jumps to a value of 1. This is a step function or Heaviside function named after Oliver Heaviside, 1850 to 1925. There's a picture of him from Wikipedia. Okay, find the Laplace transform of the Heaviside function u of t minus a. The Laplace transform of u of t minus a is going to be, by definition, the Laplace transform u of t minus a times e to the negative st. But again, remember, Laplace transform only kicks in at t equals a. Before then, it's 0. So this is the same thing as the integral of e to the negative st from a to infinity, because everything before that is 0, and that has value e to the negative as over s. In the same way, we could show that the Laplace transform of u of t minus a times f of t minus a is e to the negative as times Laplace transform of f of t. Express this step function in terms of the Heaviside function. F of t equals 0 for t less than 5, and 7 for t greater than or equal to 5. Okay, so again, here's the Heaviside function, u of t minus a. So we can see, we can see that a equals 5 here. So we're looking at u of t minus 5. It's 0 between 0 and 5, and it's 1 for t greater than or equal to 5. We don't want it to be 1, we want it to be 7, so we just multiply both sides by 7. 7 u of t minus 5 is 0 for t between 0 and 5, and it's 7 for t greater than or equal to 5. Let's find the Laplace, let's express this in terms of the Heaviside function. F of t equals 3 for t less than 5, and 9 for t greater than 5. Okay, so here again is the Heaviside function. We don't want this to be 0 and 1, we want it to be 3 and 9, so let's just add 3. If you add 3 to the Heaviside function, now we've got it equals 3 for t between 0 and 5, and 4 for t greater than or equal to 5, which is close. We just don't want it to be 4, we want it to be 9. So we just need to multiply this by a constant. 3 plus 6 u of t minus 5. It's going to be 3 between 0 and 5, and it's going to be 9 if t is greater than or equal to 5. How about this? Express this in terms of the Heaviside function. F of t equals 3 for t less than 5, and 10 plus y squared for t greater than or equal to 5. Okay, so for u of t minus 5, again, looks like this. 3 plus u of t minus 5, we talked about that earlier. We saw that a moment ago. It's going to be 3 for t between 0 and 5. It's 4 for t greater than or equal to 5. That's not good enough. We want it to be 10 plus y squared. We don't want it to just be 4. So let's multiply u of t minus 5 by 7 plus y squared. That way, the function is 3 when t is less than 5, but when t is greater than or equal to 5, then we get all of this stuff. We get 10 plus y squared. Find the Laplace transform of u of t minus 6 to the 4th. Okay, here's the definition of the Laplace transform. Here's the formula for the Laplace transform we saw for Laplace transform of u of t minus a, f of t minus a in general. Okay, in this case, we can see that a equals 6. So we'll plug in a equals 6, and we end up with this formula. And now, when we compare these formulas, we can see that f of t minus 6 is t minus 6 to the 4th. So that means f of t is just t to the 4th. We know how to find the Laplace transform of t to the 4th. So the Laplace transform of t to the n is n factorial over s to the n plus 1. Laplace transform of f of t is, in other words, Laplace transform of t to the 4th, and then based on this formula, it's going to be 4 factorial over s to the 4th plus 1. In other words, 4 factorial over s to the 5th. So let's put all the pieces together. Laplace transform of u of t minus 6, f of t minus 6, based on the formula we saw earlier, that's e to the negative 6s times the Laplace transform of f of t. And in this particular case, Laplace transform of f of t is 4 over s to the 5th. So the Laplace transform of this function is e to the negative 6s 4 factorial over s to the 5th. Okay, let's do it. We're going to do it. We're going to solve this initial value problem using Laplace transforms. dy dt equals negative y plus u of t minus 3, y of 0 equals 2. So we can rewrite this as dy dt equals negative y for t less than 3 and negative y plus 1 if t is greater than or equal to 3. Okay, so we're going to take the Laplace transform of both sides of this equation, and we end up with this. We can simplify. We've seen before the Laplace transform of dy dt is s times the Laplace transform of y minus y of 0. This equals negative Laplace transform of y, because we can pull the negative signs to the outside, plus the Laplace transform of u of t minus 3, which is just this over here. Okay, so y of 0 is 2. We're going to plug in 2 for y of 0. This is what we end up with. So again, this is what we had from the previous page. I'm going to get the Laplace transform of y, get both of those on this side, and move the 2 to the other side, sorry. Let's see. So we can factor out Laplace transform of y. We have s plus 1 times the Laplace transform of y equals 2 plus e to the negative 3s over s. Divide both sides by s plus 1, and we end up with this. If we were to use partial fractions, we'd be able to express it like this. 2 over s plus 1 plus e to the negative 3s over s minus e to the negative 3s over s plus 1. Okay, so lastly, we just want to take the inverse Laplace transform of both sides. So we want this stuff on the right side of the equation to be a Laplace transform of stuff. So we can take the inverse Laplace transform of each side. Oh, we can express e to the negative 3s as the Laplace transform of stuff. That's good. That's just u of t minus 3. But we don't have anything on the sheet, anything we've seen on a formula sheet that enables us to represent this, e to the negative 3s over s plus 1, as the Laplace transform of stuff. However, we've seen before that when we have e to the negative as times something we already recognize as a Laplace transform, we can use this formula. The Laplace transform of u of t minus a times f of t minus a with e to the negative as times the Laplace transform of f of t. Okay, this is the form we have. Okay, check this out. We can write this function in this form, e to the negative as times the Laplace transform of f of t. So again, we're going to use these formulas. So we can rewrite e to the negative 3s over s plus 1 as e to the negative 3s times 1 over s plus 1. And now we've got it. This is e to the negative 3s times the Laplace transform of some function. What is 1 over s plus 1, the Laplace transform of? It's e to the negative t. So e to the negative as times the Laplace transform of f of t. That's e to the negative 3s times 1 over s plus 1. In other words, e to the negative 3s times the Laplace transform of e to the negative t. Okay, we're ready to put all the pieces together. This is what we've seen from the other side. So we're going to apply the formula we've seen with a equals 3 and f of t equals e to the negative 3, e to the negative t. So e to the negative 3s times the Laplace transform of e to the negative t, that, based on what we've seen before, is the Laplace transform of u of t minus 3 times f of t minus 3. In other words, it's the Laplace transform of u of t minus 3 e to the negative t minus 3. Okay, we're almost done. We're almost there. So the Laplace transform of y, okay, with this we've seen before. You break this up using partial fractions, you end up with this. And it turns out that it's Laplace transform. This is the Laplace transform of 2 e to the negative t. This is the Laplace transform of u of t minus 3. And this is the Laplace transform of u of t minus 3 e to the negative t minus 3. So now we're just about done. We take the inverse Laplace transform of each side, and we get, this is just going to be turned into y, and all this stuff is going to be 2 e to the negative t, u of t minus 3, minus u of t minus 3 e to the negative t minus 3. When we factor out the u of t minus 3, we end up with 2 e to the negative t plus u of t minus 3 times the quantity 1 minus e to the negative t minus 3.